to be quite a tough day for us because it's not only the morning session, but you know we also have an afternoon session. And then I hope that you'll not sort of be completely sort of the oversaturated with all this stuff. But there are two stories today. The morning story is about the stress concentration. And this story is, of course, it's one of the questions for your exam. It will be about the stress concentration. So I would like just to sort of highlight the things which you really have to understand and explain in the course of examination. So let's sort of begin. So then I have to introduce to you the idea of stress concentration, and of course I hope that you'll sort of be able to explain it in the exam, and then we'll consider the stress concentration in the case of the extension compressions, and it's called axially loaded members. Then it's going to be shafts, in torsion, and then beams, and then the exercise session. And then I have to tell you from the beginning that in the list, I remember I told you that the exam is oral, and then if you draw the question stress concentration, there are some bullets, there are some sort of the points which you have to highlight. And one of these bullets, I can tell you right now, it will be just the solving the problem in stress or illustrating solving the problem in stress concentration. So I'm not going to be more detailed in this, but this is so the problem which we are going to exercise. These exercises, you see, we have these 3 exercises. Then they will be quite relevant, and also I spent some time in solving one more exercise. So what is the stress concentration? So this is something which is very dangerous and something which is absolutely unavoidable in the engineering. So we don't like stress concentration, but we have somehow to cope with it. And the point is that if you have any inhomogeneity, let's say you have the point there the force is applied, you have some kind of geometrical features, kind of the step change in the radius, step change in the angle, or some just whole material changes. If you have this micro inhomogeneous materials, also due to the fabrication, let's say welding or gluing, then whatever sort of the spoiler you put into the structure, and it's absolutely inevitable, you just can't avoid it, then you immediately have the jump in the stresses. And this is something which is very, very bad, because at the first thing, as you remember, the idea of mechanics of materials, strength of materials, is just to ensure the reliability of the structure. So we want to be absolutely certain that the structure will not fail. And structure fails as soon as the stresses exceed the critical value, the value at which we have some fracture or buckling or whatever. So then we have to ensure that it's not the case. But this stress concentration, and here there are these two, these pictures. So the first one is you have this teeth connecting in this the two rolls, and then this is the stress concentration. And then this picture below, it's something which is quite sort of this is what all engineers deal with when they do finite element analysis. So here we have the distribution of stresses in all likeness. It's the von Mises equivalent stresses. And then I'm not sure that I can see what was the actual kind of load, but the thing is that you have here multicolor plot. And this is something which is not very good, especially then we have this hot red spots. So these blue areas, it just means that the stresses are fairly low. So there is a scale here, you probably can't see it. I can't see it either, but it's just from the viewpoint of the qualitatively assessment. So when we have this blue areas or greenish areas, it's okay. Their stresses are not that high. But these hotspots, these red areas, this is the areas where we have the high stresses. And most unfortunately, these high levels of stresses, they are virtually always associated with the stress concentration. So we have to somehow predict it, model it, and avoid it. So the first thing, which is sort of the very, very dangerous, is fatigue, and this is what we'll discuss in a bit later in our course. But it's also possible that we could have immediate failure due to the stress concentration. And here, this is what could happen. So this is just, of course, it's a testing. I don't think it's something which was framed in real life. But you see what happens is that you have this imitation of the flight of this aircraft. And then you have, of course, this sort of huge forces produced by the flow of air. And then you have this very typical connection here, these bolted connections. And if you travel on plane, you see that there are a lot of on the wings. And then this guy, this is the typical stress concentration. So then if we do the finite element analysis, so this is just we take here this the part, and then we apply the shear stresses and normal stresses as shown in this picture. Then we can immediately see that again we have these blue areas. There we have very low stresses, and then here we have these high stresses, which after all they generate a failure. So then this stress concentration, then you have this bolted connection, you have these things. And then the stress concentration is very dangerous for all the kind of loading, for static loading, for dynamic, and for fatigue. But it is especially critical when we consider the brittle material. So for all these, for the statics, dynamics, and fatigue, if we have brittle material, then we are in a real danger. Then if we do the static loading of the ductile material, then it's something we can tolerate, but I will explain with some extra diagrams in a second. But if we do dynamics, then just as we discussed yesterday, it is also an issue for these materials which may have plastic deformation, because if you have very fast loading, then dynamics prevent development of plastic deformation. And fatigue, it's a real problem, no matter whether it's brittle material or ductile material. And then before we go to this slide, I just want to show you what I have to the drawn. So of course, it's a pity that we don't have the possibility to use a blackboard and have this sort of a face-to-face lecturing, but nevertheless, here I have just sketched things, and this is the essence of stress concentration. And here I just want you really to take your time, try to understand. It's not that difficult. And then if there will be any questions, then please interrupt me, raise your hand, or just interrupt you with unmuting your mic, because I think it's very important to be crystal clear with these things. So if we have there is the simplest possible case. We have this kind of let's say plate which has a rectangular cross section, and then we apply the force, and we draw the hole here. So this is the hole. And then, as I have already mentioned to you, we have the stress concentration around the hole. So I jump backwards, and then one slide back. So this is the picture. And then you see that if you do the cross section, if you chop the specimen relatively far from this hole, then you see it's more or less the same color. So it's sort of the greenish, something like this. Then if you come a bit closer and you chop it here, then you have this green areas, and also you have this blue area, which means that you have here the very low stresses. But I think it's sort of intuitively it's quite clear, because if you come very close to this hole, then obviously the axial stress here will be just zero. So if we return to this picture, so now we are I'm sitting in just in the middle of this hole, so I just cut it like this, and then, as I have demonstrated, we have already seen, we have the local increase in the stress. So first of all is that if we take the resultant of the stresses acting along this line and along this line, then of course these stresses altogether, they have to balance the force. So this is the thing. So here we have this AC, it stands for the cross-sectional area here, and when in the next slide we'll just again repeat it, but we have this sort of the weakened cross area of cross-section, and then of course the total resultant of stresses must balance the force. So this is, I think it's obvious. Then we can come up with what is called nominal stress, and the nominal stress is just you take the force and divide it with this weakened cross-section. So then you do this thing, you completely ignore this kind of the distribution of the stresses. You just say, so the nominal, it's just you have a reduced cross-section area such that you don't have this hole. And then this is the nominal stress, which is, if you don't have this stress concentration, it would have been uniformly distributed. Then we have in the real life, with this stress concentration, we have the maximum stress just at the edge of the hole, and we have minimum stress, which is sort of quite far. And here probably this picture is not absolutely perfect, because in fact this stress concentration is very highly localized. So here I have shown it as a little bit sort of a spread. But again, if we return to this picture, then it decays very fastly. So you see, if you just step a little bit inwards, then the stresses decay dramatically. So it's really very local phenomenon. And then this maximum stress in the immediate vicinity of this point, it's this stress concentration factor times the nominal stress, and of course the stress concentration factor is much larger than 1. 3, 5, or whatever, depending upon the shape of the hole and the relation between the radius or diameter of the hole and the width of the specimen. But then also what is very important to notice is that this minimum stress, the stress which acts at this edge here, it is less than nominal. So if you have some increase of the stresses nearby the hole, then you have some drop in the stresses far away from the hole, simply because you have this condition which must be fulfilled. This is equilibrium condition. So the force resultant of all the stresses acting along this line and this line must balance this force. And then, as we are absolutely certain that we have maximum stresses here, then interestingly enough, we have smaller stresses here. So here they are larger than nominal, and here they are less than nominal. Does it make sense? Any questions about it? No. Good. So then we go back to the slides. And then we have more or less the same picture with the It's of course from this book of mechanics of materials. So it's more or less the same story, but a bit nice in 3D. So we have this force, and then we have this distribution of stresses, and then what we have this stress somewhere here, far away from the stress concentrator. So there's just this force divided with the area, or it's B is this width, and T is the thickness. Then we take the average stress or nominal stress in here, and then as I showed you in the previous handwritten slide, it's the force divided with this reduced area. So here it's a bit confusing because here A and here it's also A, but here A, it's the area measured here. And here this A is the area measured where you have this hole. And then of course it's C times T, and C you have here C half and C half. So that's the total length is C, and the width is thickness is T. So it's this one. And then the definition of the stress concentration factor is the maximum stress divided with this nominal stress. And then immediately you can see here the dependence of this stress concentration factor upon the ratio between the diameter of the hole and the width of the specimen. And then you see it's quite interesting, but probably it's something that you can sort of understand, that if you have broader and broader, larger and larger hole, then effectively the stress concentration factor reduces. But it's simply because you have the nominal stresses becomes larger, right? You have the area becomes smaller, and then the nominal stresses become larger, so that the stress concentration factor reduces. So if somebody is sort of not quite convinced by this, just raise your hand and we'll discuss it, because I think here these things, that I hope that they are quite convincing, but probably I'm not quite sort of convincing in explaining these things. So if you have some doubt, just sort of let's discuss it. So if you make the hole bigger and bigger, the stress concentration factor becomes smaller and smaller. And the reason for this is that we have the increase in the nominal stresses. And the stress concentration factor is the ratio of the maximum stress and the nominal stress. But what sounds a little bit paradoxal is that if you make the hole smaller, smaller, and smaller, then the stress concentration factor rises. And if you have infinitely small, invisible, let's say, hole, then your maximum stress appears to be 3 times larger than the nominal stress. So you have this factor 3. And then you, of course, I think it's at least some of you will ask the question, so how do we know this thing? So is it possible to measure it, or actually how it is assessed? And the answer is that this stress concentration is one of the very important subjects in the mathematical theory of elasticity. So this subject, it's really mathematically very much advanced, and this is sort of beyond the scope of our curriculum. But and it gives you the mathematical tool to predict this curve, and it's based on what is called the functions of complex variables. It's complex valued functions of complex variables. So it's a very complicated thing, but then what you get, for example, for this simple case, you are able to have the exact analytical solution of the problem of stress distribution. And in this exact analytical solution, this ratio D divided with B stands as a parameter. And then you may just take this parameter to the limit that it equals 0. And then you have this magic number 3. And of course, you cannot do the experiments for this sort of like a hole made by a needle. But if you have some sort of recognizable hole so that you can do the measurements, then it's quite amazing how accurate this prediction is. So then if you are somewhere here, then you are able to put some tensometer here to measure the stress, and then you compare the stress with the theoretical prediction, and it perfectly it matches. So that's all fine. Yes. Any questions about it? So now think about the examination that you are supposed to explain these things in the convincing manner. Now you can see that here we have a lot of the parameters, a lot of uncertainties, because here this is the circular hole, but it can be rectangular, it can be triangle, it can be ellipsoidal, right? So you have plenty of different shapes of this hole, and for each of the shapes you have the solution which gives you the curves. Just let me show this kind of curves. So here this is the tables, but I think it's not what we have to do immediately. Just for your information, we have uploaded plenty of similar curves from the book Design of Mechanical Systems by Norton. There these stress concentration factors are presented in this graphical form for different cases of loading and for different concentrators. So it's huge work which was summarized maybe something like 100 years ago and then verified with experiments. So actually what happens that if, for example, here, if we have this change in the width, so it's not a hole anymore, it's just change in the width. So you have here a bit thicker, and here you have thinner. Then you have this transition radius, and then what happens is that a lot depends upon, of course, upon this ratio difference. So how steep is this change from B to C, but also you have very sort of the strong influence of the ratio of this radius to what you have here in the end. And all these curves, as I say, these curves were obtained using this mathematical theory of elasticity. They also verified by the experiments, but you can also do these kind of things using the finite element method. So one of the possibilities in the using finite element method is that if you introduce mesh and then apply these forces, then you are able to calculate stresses everywhere in this specimen. And then in particular, if you come to these points, then you see that this sort of the stress concentration factor agrees we find from the finite elements with these predictions. Yes. So now if you just let me go a little bit back here, then what actually happens is that let's now think about the concentrator not in the shape of the circle, but now let's say that we have ellipse, so that let's say that we maintain this diameter, this width, the same, it's a D, but we just sort of squeeze this hole a little bit towards the this axis. And then if you do this, then here in this point and in this point, you have the larger and larger curvature. And then this increase in the curvature. So if you go down to the extreme, so if you say that you maintain this width, but this distance comes to 0, then this maximum stress turns to infinity. And this is the mathematical result, which has been obtained, as I say, something like maybe 100 years ago, 150 years ago. So this is something which is very well sort of known. So if you take this kind of the crack, because now it will be looking more like a crack. So you have this the same width, but in this direction it's nothing. Then you have infinite stress concentration. And then if you have infinite stress concentration, then you're in a big trouble, because no matter how small the force is, in this point you have infinitely large stresses, and you have a fracture. And in order to see what happens there, let's again go to this handwritten notes. They're meant to be put in the blackboard with probably better explanation. And now let's take the look at here. There we have difference between the performance of the brittle material and ductile material. So if we say that this specimen is made of brittle material, let's say cast iron or glass, let's say, then as soon as we have it's the same holds true for this circular hole, not necessarily the crack. So if we have this hole, and then we increase the force, then of course we have increase in this maximum stress, and then as soon as this maximum stress attains the value of ultimate stress, you remember, I hope you remember this diagram. I think you had it with Joran Kepler. Then this is the uniaxial loading, then you have this epsilon, and here you have stress, and then this is brittle material. So you have a linear performance, and then you attain this point, and that's it. You have the brittle failure of material. So this is ultimate strength. Then you see what happens. So you have attained here this ultimate stress. Then you have a crack here, and then this crack, as I told you, it gives you the infinitely large stress concentration coefficient. So it means that it will be the ultimate stress will immediately pierce through this thickness, and then you have instantaneous failure of this specimen, because as soon as you attain here this ultimate stress, then you have infinitely large stress concentration factor, and you have a fracture like this and fracture like this. So this is very bad, and this is why we don't produce any bolted connections for the pieces of glass. So if you have two pieces of glass, I don't think that you can consider seriously to drill the hole and then to put a bolt to connect two pieces of glass, because it will be hopeless. It will fall into pieces immediately. But if we have a ductile material, then what happens is that you have this yield phenomenon. And again, I hope that yield, it rings a bell for you, because this is what you have discussed with Joran for sure. And this yield phenomenon means that you have this irreversible plastic deformation. So if you remember, so if you just take the specimen and you go first, it's linearly elastic, then you go to this yield deformation, and then you have this yield deformation. So then if you stop here and you drop the force, it will go strictly parallel to the first part of the diagram. So now let's take a look at the performance of this ductile material in the case of the stress concentration. So you have the increase of the force, and then you have, so it happened that you have hit the yield stress. So now our sigma max becomes the sigma yield. But in contrast with the brittle material, there is no fracture, because we may safely keep on increasing this force. And then please see, of course, it's not a very nice drawing, but I hope you are able to follow this logic. So what happens if you just hit this yield point? So now it's in this single point you have the stress which equals to the yield stress. There is no fracture. Then you continue increasing the force, and then this force must be accumulated by the stresses here. And then the stress at the tip here, it cannot be larger than the yield stress. So it remains the same. But in order to accommodate the increase in the force, these yield stresses start to penetrate into the material, so that we have here, and also here, of course, we have something which is called plastic zone. So we have the transition of the material from the linear performance, from the elastic performance, to the yield. So we have this plastic zone which develops in this vicinity of this point and this point. And there is no fracture, because you have this huge possibility for the material to deform without having any crack. So if you keep on increasing this force, then what happens? You have gradual increase in the plastic zone, and then you can immediately see that the stress concentration factor for the elastic plastic deformation will decrease, because the maximum stress cannot be larger than yield stress, and the nominal stress keeps on increasing. And then the real the collapse of this specimen will occur. Then the plastic deformation will occupy the whole cross section here and here. So you have, by the end of the day, you have uniformly distributed yield stresses. And then in this case, of course, you have, so now you have very, very large deformation, but the stress concentration factor turns to 1. So in the brittle material, the stress concentration factor, as soon as you attain this ultimate stress, it jumps to infinity, and it's death of the specimen. In the ductile material, if you keep on increasing the force, the stress concentration factor becomes smaller and smaller, and by the end, it just becomes 1, but there is still no fracture. Does it make sense? Any questions? No questions. Okay, so I hope that you explain these things in the...
I have one question.
Yes, please. Yes, sure.
Can you please explain the plastic zone again?
Yes, so we have this diagram for the ductile material. So then you see that if you do this extension test of the specimen, we have the elastic deformation, and then we have huge sort of the zone of the plastic deformation. So the stress doesn't increase, but the deformation increases. So now, if we have attained this, what is called fiber yield. So fiber yield, it just means that our maximum stress attained this yield stress at this point. And all the, so this here we have plastic deformation, here and here, but anywhere outside this point, we have elastic deformation. And then we continue to increase the force. Then this arrow in the vicinity at this point, it cannot be any longer, right? The material cannot have larger stress than yield stress until it comes that far. So it means that this stress is kind of frozen at the level of yield stress. But we have to accommodate the increase in the force. And it just means that all other stresses, they are able to grow and they increase. And then next fiber, let's say, comes to the yield level. And it cannot be any higher. So it's ultimate level of stress. And then you increase the force. And then this plastic zone goes further into the material of the specimen, not only in this direction, but also in this. So it's it will be like, so the plastic zone, just let me show you. Here, the plastic zone is something which emerges, develops like this. So it becomes sort of, it goes in this direction, but also it goes in this direction. Make sense?
Yeah, I think so. I've got a question as well.
Yes, please. Yes, please. Go ahead.
Have you got an example of what material could have a plastic zone like that?
Oh, it's all the steel, structural steels. So if you take any what is called mild steel, then you have it.
But does that say that at no point you'll get a fracture then? It will only ever deform plastic, or will
No,
at a certain point it will break?
So I see. So if you take the cast iron, then and you draw this hole, and you apply the force, then it's very sort of a dangerous thing, because you almost for sure you will have fracture. So now if you have this mild steels, then it's again, this is the experience accumulated in 100 years, that this development of the plastic deformation, this generation of the plastic zone, it sort of smears out the stress concentration. So and then we will be no fracture. Instead of having this crack, which sort of pierces the specimen and kills it, you have just this plastic zone, which is, again, it's kind of constrained by the neighboring elastic zone, because elsewhere you have low stresses, and then the material nearby, it performs elastically. So it's very sort of the innocent thing. So it's not critical for the structure if you have this plastic zone. So in principle, if you like, you can think about kind of the training of the structure. So you manufacture the structure, you have this bolted connection, and you put it into action, and then you have some kind of the load, and you have this plastic zone. Then load disappeared, but the plastic zone is still there. And then if you repeat the loading, then there will be no crack, no fraction. Is it more confusing or than explaining?
No, that makes sense. Cheers.
Good.
I have a question.
Yes, please.
So,
yes, please.
The nominal stress defines when it's going to crack. or because the maximum just can be the yield stress?
I'm sorry, you're asking about the nominal stress in which story? Because
in the last
in the last story.
Yes.
In the last story, the nominal stress is just brutal force divided by the actual cross-sectional area.
Yeah.
So you just take the force, this one,
yeah.
and then you divide it. So if we return to this nice picture from the book, you just divide this CT, and you see this CT. You have C half and C half. So this is this length plus this length, and then T is the thickness. So the nominal stress is defined like this.
Okay, but when does it crack then?
If you have the ductile material, there is no crack.
But if you have the elastic, like steel material, when does it crack then?
Which material, sorry?
The steel.
For the steel, yeah, okay. So you see, what happens is that you have it's called, in some cases, it's what is called plastic hinge. So what happens is that if you sort of keep on pushing with the force, so that the end result, I just didn't show it here, but you can easily imagine that the end result will be that you have uniform distribution of yield stresses here and uniform distribution of yield stresses here, right?
Yeah.
So then, and this is definite value of the force. So then now let's see what's going to happen. If it's like this, then so far, then you have this kind of the non-uniformness. You have this plastic zone confined by the surrounding elastic zone, so that the deformation of this specimen is confined. It's quite small. But if you have total plastic deformation across the cross-section, then you have very, very large deformation. So then this this specimen may yield, so it may really become maybe 30% longer than it was before. And then, of course, it means that it's not functional anymore. But there will be still no crack. The crack will be only if you go beyond this level. If you go beyond this point, then you'll have necking here, and then you'll have a fracture. But this is something which is not allowed in the real life, of course.
Okay.
I have a quick question, Sergey.
Mm-hmm.
I'm a bit confused how you find the maximal stress. You wrote something about the stress concentration factor times the nominal stress.
Mm-hmm.
But you also write here that the maximal stress is equal to this yield stress. So are you supposed to just calculate it or look it up for the material?
So the maximum stress, of course, you could calculate it, but this is exactly where all this all these diagrams come from. So all these curves, they give you the stress concentration factor for all possible types of concentrators. And these stress concentration factors, they are found from the mathematical theory of elasticity. They are verified by the experiment, and the finite element method is checked as a sanity check to match these values of stress concentration factor from the mathematical theory of elasticity. So if we are after nominal stress, it's very simple. It's just the force divided by the netto area.
Okay, so there's no need to look it up for material or calculate it. You just look it up in the diagrams.
Yes. So actually, the stress concentration factor is insensitive to the material. So what you say is that you believe that your material is isotropic and elastic. Then, and this is actually what you do in finite elements, and also what you do in the theory of elasticity. So you do this mathematical analysis. You've got this stress concentration factor. Then you multiply the stress concentration factor from the tables by the nominal stress, and then you have this maximum stress. And now you take your specification of material and you see whether it's brittle material or whether it's ductile material, and then you sort of do your engineering assessment whether it's go or no go to manufacture the structure.
Right, thank you.
More questions? Yes. Yes, I think I saw the hand. It's Jonas.
So K is always insensitive. It's always a constant.
So it's well, yeah, it's constant, determined by the geometry. It's
Okay,
insensitive to the material.
Yeah. So it doesn't matter if the material changes in size or.
No. That's
always the same.
You see the change in size. It's not a change of material. It's change of the structure. Change in radius, change in width. It's the change in the structure.
Okay. Yeah.
The change in material is whether you take the sort of high quality steel with the yield stress 700 megapascal, or mild steel, which is way cheaper, with yield stress 350 megapascal.
Okay, I was just a bit confused then. Yeah.
Good. More questions? Right. So now I'm just going to to confuse you a little bit, because this sort of the division between the brittle and ductile materials, this is something which we have in the ideal world, but the really sort of the dark side of the story is that we are not always 100% sure that our ductile material is indeed ductile. So first of all, we in the design of any structures, we avoid using the brittle materials if we are dealing with the stress concentration factors. So the example is that, of course, we can use cast iron in some situations, but it's not a very good idea to drill holes. And we definitely don't use glass for structures exposed to kind of the loading. But we are very happy with ductile materials as isotropic, but also anisotropic materials as wood, for example, because we know that these ductile materials are able to kind of swallow this stress concentration, because this is very important, that as soon as you have this plastic zone, the stress concentration factor goes down. But there is no guarantee that your ductile material will not sort of become brittle. And the cases, simple cases, are the change in the temperature. So if you take the material, the steel, and you make it quite cold, sub-zero, much sub-zero, then it turns to be brittle. It loses its ability to perform plastic deformation. And if you apply dynamic loads, if you just sort of apply loads very, very fast, then it also loses the possibility of this plastic deformation. And then also, if we have fatigue, if we have very, very low stress levels, but they are repeating, we may also have this brittle fracture of ductile materials. So it's not all sunshine. But anyway, this is that's how it is. But this is something which we have to be fully aware of, that if in our sort of the standard testing, quasi-static testing, we see a very nice yield deformation here, then it doesn't guarantee that it's going to be equally nice in the real life. Okay. So now, Do you feel like having a break, or you are quite happy to move on? Or probably you have different opinions. So then let's say have a short break. Let's resume at quarter past 9. Okay. Quarter past 9. So we continue. Maybe there are some questions after the break. If not, then let's just move on. And then in this next slide, you can see these curves which were obtained, as I say, using this mathematical theory. So here you have this rectangular cross section of the specimen, and then you have these parameters, the change between C and B, the difference between C and B, and this radius. and then, of course, your stress concentration factor is sensitive to both these things, but as we discussed, it's not sensitive to the material. There are no properties of material. It's only properties of geometry. And then the stress concentration factor will be the same no matter what is the material you're going to use to manufacture this thing. But also important thing worth to be noticed that if we collapse this R to C ratio to 0, then the stress concentration factor goes to infinity. And this is what I have already mentioned to you. Then this is another story. This is just this more or less the same thing, but for the shaft. So if you have a circular bar here and a larger one here, and then again you have this radius, then you have this kind of the curves. And then if you just I just probably try, probably not. So in the Moodle, there are plenty of diagrams like this uploaded. It's not, it doesn't mean that you are going to use them. This is just to give you the sort of overview of these things. But you can imagine how many graphs like this we may sort of be produced, because there are a lot of possible concentrators, shapes, relative dimensions, and so on and so forth. So this is a, let's say, endless story. But if you do the mathematical theory of elasticity, then you have what is called conformed transformations. So you have one solution, and then this solution is equally valid for the very broad range of problems. So it's not that difficult. But if you do finite elements, then I'm afraid for each particular geometry and for each particular material properties, you have to run your finite element code. Now this is the example. I'm not going to do the numbers here, but this is just again how it's formulated. So we have the specimen, and we know that this specimen has two stress concentrators, a hole and this fillet, and then we are provided with the dimensions. So what is the width, what is the thickness, and how what is the material properties. So this is the ultimate strength. And then what we need to do, we need to find the stress concentration factors, and then for given force, what is the safety factor. And the way to do it is, of course, we have this concentrator, the hole, and then we know that this is the ratio is 0.2. So we just draw vertical line until we cross this curve, and then we read the stress concentration factor. Then take the nominal stresses, multiply with stress concentration factor, obtain the maximum stress, compare with the ultimate strength. Then if we have this fillet, then we do more or less the same. We are provided with these dimensions, and you see that what is important is that these curves are non-dimensional. You see the stress concentration factor is non-dimensional. It's a ratio of maximum stress to the nominal stress. Then here you have R to C ratio, and here you have this family of curves for different values of B divided by C. So then for the given set of parameters, we spot this point 10 for R to C ratio, and we come to the 1.3 B to C ratio. And then we read the stress concentration factor. And then again, if you have something in between, then you do just interpolation between these curves in order to find this stress concentration factor. But again, given the kind of uncertainties with the material properties, it's not that important to find the stress concentration factor accurate up to the third digit after the comma, so just to do the assessment. Then if we go to the shafts, then it's basically the same story. So what happens is that we have the shaft which exposed to the torque, and then we know that the shear stresses are defined by this formula. So this is the torque, this is the distance from the axis to the point there you want to measure the stress, and this is the polar moment of inertia. So now if we are sitting at the surface, then this small r is just the radius of the shaft. And then if we take the this thicker diameter, then we have this distribution of shear stresses. They are maximum at the surface and they are zero at the axis. Then if we have the smaller radius, then we have this distribution. Of course, shear stresses at the surface here are larger than here because the moment of inertia is way smaller here than here. So this is why this stress is less than this one. But in the transition zone, in this zone, the stresses are even higher. So in principle, it's exactly the same story as in the axial deformation. And then we introduce the stress concentration factor in exactly the same way as in the for the axial extension compression. So we just take the nominal shear stress and multiply it by the stress concentration factor. So it's just one-to-one, the same as there. So here, this polar moment of inertia, it's this, have this D1, and R is also D. So that's how it is. And then we have with the tables or graphs showing the stress concentration factor as a function of the same things, this ratio of D2 and D1, and the ratio of radius, this radius to D1. And then it's the same story. So if we go to the very sharp change, then the stress concentration factor for shafts, it goes to infinity. So it's just the same thing as for the axial extension compression. And then, yes, and this is also the example. So if we have now the combined loading, so if we have the, you see here, we have the torque, and we also have the extension. So then we have the stresses produced, the shear stresses produced by the torque, and we calculate the nominal stress, and we calculate the stress concentration factor. We multiply stress concentration factor with the nominal stress, and we find the maximum shear stress. Then we take separately the axial extension. We take this diagram, and we do the same. So, but this is the important thing, is this stress concentration factor is for torsion. It has its own value. And here the stress concentration factor is for axial extension. It has another value. So this K here is not the same as K here. So they are two different things. But the thing is that we calculate maximum shear stress. We calculate maximum normal stress by this thing, And now we have to assess the strength. We have to give our conclusion, whether it's dangerous or not dangerous. Then we use this, and I think this is in this slide, I think this is the typo. So I think you have to do with what the third bullet just says, that you have you determine the principal stresses and then a von Mises equivalent stress in this region, in this transition region. And then this von Mises stress is just, I think it's something like sigma squared plus 3 times tau max squared. But again, so this is something which is not quite important for us, except for if we have this combined loading, we have to do assessment of the strength using this von Mises criterion. And then if the strength condition is fulfilled, then it's okay. If it's violated, then we cannot sort of manufacture this because it will fail. So here the add-on here is just that if we have the combined loading, we have to do the analysis of stress concentration for each of the loading individually. You see we have here what is called superposition. And then we have to do assessment of the strength using the equivalent von Mises stress. Any questions about it? No questions. Okay. So this is kind of the superposition principle for the combining torsion and the axial deformation. And now our last example, last case, is the hole for the beams. So if we have this bending, and now we also have the specimen with the hole, and we have now the bending. So the first thing is that we do this assessment of stress concentration. In bending, we ignore shear stresses. So in principle, we have, if you remember, probably from what you had with Joran Kepler, you have this what is called pure bending, then the shear stresses are 0, and you have the non-uniform bending. Then you have both normal stresses and shear stresses. And then the analysis of stress concentration for the beams with the holes is only concerned with the pure bending. So we say that the influence of shear stresses is negligible. And then the thing is that we have linear distribution. Probably you remember this. We have linear distribution of the normal stresses along in the cross section. So here you see here this is a dotted line like this. So if you don't have this hole, then it will be just conventional straight line distribution, and of course you have maximum stresses at the edges. You have here maximum stresses in extension because of the direction of the moment, and here you have exactly the same maximum stress in compression. So now if we introduce this hole, then what happens is that you have increase in the stresses at this point and at this point due to the stress concentration. So stress concentration also is visible in bending. And then there may be two scenarios. The first scenario is that we have the increase in the stresses due to the stress concentration, which is less than the maximum stress due to the kind of the conventional bending. And alternatively, you may have the situation that the hole is quite big, that the stresses due to the stress concentration now become larger than the stresses in the bending. So does it make sense? I'm not sure that I have explained it quite clearly, But probably if you just ask questions, then it will be easier for me to understand where I didn't explain it okay. So do you see the difference between this picture and this picture? So the moment is the same. Here we have a relatively small hole located close to the neutral axis, because here you have kind of a balancing of two things. The first thing is that, of course, if you have a hole, then you have the increase in the stress as compared with the nominal. But if you have a small hole, then it means, and it's located at the neutral axis, of course, here this important statement that the hole is located at the neutral axis. So if you come closer to the neutral axis, the stresses themselves become small, right? Because it's bending. And the neutral axis, the stresses are zeros. So then you have this trade-off. So if you make the hole smaller and smaller, then you have increase in the stresses due to concentration. But on the other hand, the nominal stresses also reduce, because the nominal stresses are calculated the closer and closer to the neutral axis. And then if there are only two possibilities, one possibility is this stress due to the concentration is less than the conventional bending stress. Then we have to assess strength judging upon the stress in this point A, or we have a situation there the hole is large, so that the stress concentration overshoots the maximum stress in bending. The nominal stress in both cases is calculated by this. So they have a moment multiplied by the distance and divided by the moment of inertia. No questions? I'm a little bit pushing here because this is something which will be, to be honest, this is something which is, in all likeliness, will be one of the bullets in the question on stress concentration. So probably I shouldn't tell you this, but in all likeliness, it's going to be like this. So please take a look at this from this perspective and make sure that you understand the difference and the challenge. So once again, it's the same moment. You have the small hole. If you have small hole smaller and smaller, you have larger and larger stress concentration factor. But the nominal stress becomes smaller and smaller because you come closer to the neutral axis. And here, if you have large hole, then at one hand, of course, you have decrease in the stress concentration factor. But on the other hand, the nominal stress grows. And it may be the case then this tendency overshoots this linear distribution of normal stresses. Okay, so hopefully you understand. And then the end result is that, just to skip all the mathematics, is that in this case, the stress concentration factor is just 2. So then if we have this kind of the situation, then the normal stresses in bending due to the concentration, stress concentration are calculated by this formula. So you have, but I mean, you immediately, you can, I think you can see that without this 2, you will have just 6md divided by this denominator. And then the denominator is, of course, the moment of inertia. So it's bh cubed minus d cubed divided with 12. So then 12 goes to the numerator, and then maximum will be d half. But then due to this 2, a half and 2 cancels out, and you have this formula. Think about it. Okay, so then the next thing is.
Can I quickly ask? Sorry.
Yes, please. Yes. So I'm a little bit surprised that you don't have any questions.
How do you determine that K is always 2?
This is something which is sort of we have to take for granted. So in the real life, it's not 2, but it sort of fluctuates around 2. So there is no harm to say that if we have large hole, then it's just 2. But this is a result which sort of validated by the means of the theory of elasticity.
All right. And with these 2 examples, is it correct to if you want to optimize it, you have to balance between a nominal stress and stress concentration?
Yeah, so you just have to, so what you're supposed to say is that you might have 2 possibilities, and then you have 2 opposite sort of tendencies. So reducing the size of the hole increases the stress concentration factor. But on the other hand, in this case of bending, it also reduces the nominal stress. So you have a product, nominal stress times stress concentration factor, and one becomes smaller and another one becomes bigger.
Yes. All right.
More questions about it? Yes, and of course, please notice so that no one expects you to discuss what's going to happen if the hole located not at the neutral axis. So this is another story which is way more complicated. So then you prepare your sort of the answer for this question on stress concentration. Then of course just know that in all the examples we have symmetry. You remember here we have symmetry, we have symmetry here, we have symmetry here, everywhere we have symmetry. So if hole is tilted out, then it becomes sort of much more complicated, and you really don't need to be so much qualified to explain these things. It's really become quite difficult. Okay, so then we go. Yes.
I have a question as well.
Yes, please. Yes.
I was just reading the last sentence on this slide, where it says, "Notice that the parenthesis is calculated at the hold edge." What is the hold edge?
Well, I think the hold edge is just this sort of the point B.
So it's not the hold, but it's the hole. Is it the spelling?
I think it's hole. Yes.
Yeah. Okay.
I think it's hole. Yeah, yes. Of course. Yeah. I'm sorry, but that's how it is. Yes, it's hole edge. Yes. More questions?
Just quickly, what is the stress beam? What does that symbolize?
Sigma B.
Yes.
This is just the stress at the point B. You see the point B.
Yeah.
And then this is the stress at point B.
All right.
Okay.
I have a question as well.
Yes, please. Yes.
On that picture, what is C? The point C.
The point C is just the point which is located outside the stress concentration zone. So if you take the point C, you see it just sort of it's outside. So then you just have the conventional formula for the bending stresses.
Okay.
So nothing happens in point C, but we are interested in point A and point B.
I just have another thing. It's just I would like to notice that it's Nicoline's birthday, and I would just like to say happy birthday.
Thank you.
Should we move on, or there are some other questions? Okay, so now we move on, and then we will take this edge notch. It's sort of the kind of similar things. I don't think there is much to discuss with this, but this is just for, and of course you are sort of welcome to consult the book about these things, but it's similar, so I don't think there is much to be said about it. So now let's take the example, and then this example I just want to take with you together, because you also have 3 exercises after the lecture. But let's just take this example together, because it will probably be helpful just also to refresh for you this fundamentals of mechanics of materials. So the thing is that we have this beam, which is simply supported, and you remember that this left edge, it's this triangle. It means that you have the immobile support. So here you have vertical reaction force and horizontal reaction force, and here you have this kind of the roller, and it suggests that at this point you have only vertical reaction force. So then and we have this force acting at the angle defined by this ratio 3, 4, and here it would be 5, of course. And then we have the hole, and all the numbers are given, and then we want to find the stress concentration factor for this case. So what we do is the first, just let me show you this one. So can you see this drawing? So what happens is, so this is the immobile support, this is the hinge support, and we have this force. So the first thing we do, we just say that this force has 2 components. It has horizontal component and it has vertical component. And then as we apply the horizontal component, we say that in principle, of course, it acts at this surface, but there is no harm for us to put it to the axis. So we have a force of this amount acting at the axis, and then we immediately recognize that the horizontal force to balance this one must be also 4p divided by 5. So then it will be in equilibrium, right? And then we see that the axial force at the location of the hole, this one is axial force at L half. So it's 4p over 5. Then we have to solve the problem with bending. So then we have this component of the force, 3p over 5. And then the first thing we do, we set up the free body diagram like this. And then we're solving this free body with this free body diagram. We calculate the reaction force R1, and we calculate reaction force R2. And here, this is the very good way to do it, is just to use the equations of moments to find these forces independently, and then take the sum of the forces as a sort of the sanity check. So then here, first I just say that I have the equilibrium around this point. So then my force R1 rotates clockwise, and then the moment is minus R1L. Then my force 3p over 5 rotates anticlockwise, so it's with plus, and its arm is L3, because here it's 2L3 and here it's L, so it's L3, like this. And then I isolate R1, and I have this p over 5. Then I do exactly the same things, but now my reference point is here, point there, force R1 is acting. And then I take my R2 times L, moment of force R2 with respect to this point, anticlockwise with plus. The moment of force 3P over 5 minus clockwise, and the arm is 2L3, this one. Then my R2 is 2P divided by 5. Then the sanity check is this R1 plus R2 equals 3P divided by 5. So these forces are found correctly. And then I do the next thing. I want to find the moment acting at this cross section. And in order to do it, I have to set up this free body diagram using our convention for the sign convention for the moments. And then if I do the balancing of the moments with respect to this point, I have my moment as a function of x is this one, R1x, or it's px over 5. And then I'm interested in the moment acting in the middle. So it's moment acting at L half. So I substitute here instead of x, L half, and I have PL divided with 10. Any questions about it? So you can do it yourself. At least you are supposed to, because you have passed exam with Johann Kepler, and this is kind of the milestone of the theory of mechanics of materials. So this setting up the free body diagrams and calculating the internal forces, it's kind of the heart of the mechanics of materials. So you were supposed to do it yourself, but I decided it would be fair enough if I just sort of hint you towards this, and then if you have any questions, maybe not now, but then you'll do your own exercises, just make a call to me and just don't hesitate to ask any question about this thing, because this is absolutely essence of mechanics of materials, and it's a prerequisite to go to the advanced topics. So now we go to the...
Got a quick question, Sergey, before you carry on, if that's all right.
Yes?
That little hole you've drawn in the middle, that's irrelevant in this assignment, I take it.
So the hole is taken in the middle because this is how the problem is formulated.
Yeah, but your calculations, if you go back to the...
My calculations, I see your question. The thing is that then I do this kind of the thing. This presence of this hole is invisible in calculating these forces and moments.
This is purely just a moment calculation. Don't take the hole into consideration.
Yeah. So the next step. So you see here we talk about, it's a good very natural question. So here we discuss kind of the equilibrium from the helicopter viewpoint. We consider this whole structure, and we are interested in the force resultants or stress resultants acting at the structure to ensure its equilibrium. So it's not the sort of the zooming into how the stresses are actually distributed. This is the story of the resultants of the stresses. And these resultants ensure the equilibrium of this body. I think this is what you've been asking.
Yeah, that was it. Cheers.
Good. So we go to this. Oh no, it's not this one. Yeah. So this is this picture again from Johnny Jacobson, and then he already he gave these things, and now this is actually why I decided to clarify this, how it's obtained, how I have this 4P5 and PL10, because he gives them for granted. And then this shear stress is not needed, because as I told you, we in this analysis of stress we ignore shear stresses. They are negligible. So then we know that our moment at the whole is this amount, and our force at the whole is this amount. Then we take the formula from the lecture, this formula, and plug our values to obtain this. Then we take formula for the normal, for the stresses and extension compression, and we obtain this. Then we have to find this stress concentration factor, this KT, and to do this we go to the diagram here, and then for point 2 we read our stress concentration factor is 2.5. Is here, and then you plug numbers, and then you've got the answer that this is the value of the stress for the given numbers. So this is the example, and probably I was too fast in explaining it, but it's more or less the whole story for the morning session. And remember that we have to move on with the statically undeterminate structures at 12:30. So it's going to be very, very long day for you and for me doing this mechanics of materials. But now let's say it's time for you to do the exercises. You have the exercises, and I think I already uploaded the solutions. So learning by doing, but then I'll be online. I think, yeah, I'll be online, let's say maybe until 11:30, because I have to prepare also for the next lecture. And then if you have any questions on the problems or on the theory, or all this stuff, then I'll try to do my best to answer. So for the time being, I'm remaining online until 11:30, and then at 12:30 we'll have a second lecture. Okay? So please ask questions if you have any, whenever you like.